So remember, this is the core set of operations that each thread in a multidimensional array of threads will execute. Okay? That's the mental model you need to just make part of your marrow, that when you write the CUDA kernel, which is the code that's executed by threads on the device, you need to specify just the tasks that each thread is going to execute, not the parallel for loop structure, which is implicit. Okay, so there's the repo. There's the instructions. So I've provided a simple example, which is just going to populate that array. Once you've got your job running, it should be a matter of CDing to the correct directory, which is that example's CUDA simple example directory, using the NVIDIA C compiler, NVCC. Remember, this language we use to code the host code is not standard C. Remember, it has those wacky brackets on the invocation of the kernel. So we need a special compiler to compile that host code. Your GNU compiler, your Intel compiler, will complain because it's not standard C. We need the NVIDIA CUDA compiler to actually, NVCC, to compile up that code. And when we modified your soft file, what we were doing is making sure that your environment included the path to the NVCC command. Okay? And then we're going to run that command just as we'd run a normal, the thing we compiled up, we'll just run it as a normal program. Is everybody able to do this? Raise your hand if you're able to complete this task. Okay. Yep, bunch of integers. It should be a printout of the contents of that array. Okay? So who thinks, now that you've seen this process of creating the host code, using CUDA malloc, using CUDA memcopy, specifying how many threads you want, specifying what each thread is going to do based on its rank, who thinks that's difficult? It's not difficult, right? Now, conceptually, there is a bit of a challenge there. What I've done is I've asserted the parallel decomposition of the parallel for loops by choosing the number of threads in a block and the number of blocks I need to do my task. But once I've done that, all I've done is partitioned my single for loop into a double for loop and then provided the instructions for the inner body of that double for loop to the thread. The thread figures out which iteration of that double for loop it's going to execute based on the thread index and the block index. So conceptually, it's not that difficult. Does that make sense? It's not really a complicated process. Which is why it always confuses me that people think this is difficult. So I just included a make file. There we go. So I could stop here, and you've seen 90% of just getting started in CUDA. But there are some wrinkles. Here we have an embarrassingly parallel task. One thread, one entry in the array. All those threads are doing different things. They're not competing for data. There's no collective reduction. There's no communication between threads. They're just real loner threads doing one thing to one entry in an array, right? But now let's imagine that we want to do a reduction on the GPU. How do we go about doing that? Or put it another way, did you look at how to do reductions in MPI or OpenMP? What was the standard recipe?
Partial sum or something. Atomic.
Atomic add, we could do that. That's going to be fancy. You can do that in CUDA. There are atomic add operators. But it's going to be slow. Because if you've got an accumulating variable and you've got 100,000 threads accessing that accumulating variable, then the accumulation and atomic add operations will be serialized. So you might as well have written serial code. Now, you can do something a little smarter and still do that, but atomic operation is one thing to do. What else can you do?
Specify a global array and store. Specify a global array and store each component into a content.
Getting closer. I had partial sum. How do you do a partial sum?
Some sort of block first, and then some sort of grid.
Mm-hmm. That's the recipe for CUDA code, a grid of blocks, and then blocks are going to do something. So tree structure sounds good, right? Tree structure sounds good. So we can do a tree reduction. But we have to remember that the tasks assigned to each block of threads has to be independent of tasks assigned to other blocks of threads. So we need not just one tree, but we're going to need a whole bunch of trees. One tree for each block of threads, right? So we can do a tree reduction within each block of threads. Why do you think we can do a block reduction in a tree reduction in each block? What do they have, all the threads in the block, what do they have access to? Shared memory, exactly. So the recipe we're going to use for a more complicated example, which is a global reduction, is a block-wise tree reduction. Okay? So let's say we've got a vector of length 1024. We'll allocate, let's say, 128 threads to each block. That gives us 8 blocks. We'll do 8 reductions. Each block will be responsible for reducing 128 entries to 1 entry. We can do that by repeatedly using shared memory to squeeze that value, sum those values down to 1 value. Now we're going to get 8 values out of this. At that point, there is no safe way to, well, the only safe way you could at that point accumulate those 8 values is by atomic operations. But I tend to, in all my codes, I have 100% avoided atomic operations because they tend not to be scalable operations. But you could just reduce down to 8 values, store those 8 values in the global shared memory, and then either carry them back to the host, copy them back to the host, and do the reduction on the host, or you can just run that reduction process again. Instead of having 8 blocks, you would just need 1 block. 1 block loads 8 values, reduces down to 1 value. Okay? Does that make sense? So, on the one hand, we have the simple array operation embarrassingly parallel. And what I've just described is probably one of the more complicated, coordinated, thread block coordinated operations you can do. Once you've got the classic embarrassingly parallel operation, and once you've got these once you've got these block local reduction operators, you've got 2 of the most important classes of operators or operations. Okay? So let's quickly review how you would go about doing the block reduction in CUDA. Well, I see some typos already. Just to reinforce, instead of tiling by one-dimensional tiling, we can have 3-way nesting of the tiling, and you can use 6-way nested parallel loops. But that's sort of beside the point. Let's talk about a reduction. So reduction is basically summing up, in this case, the entries and the values in an array. In pseudocode, we have to think about what is the task every thread is going to execute. Not just individual threads, but every thread will run through the same sequence of instructions. So the thread is going to need to know its rank within the thread block, its thread index, right? It's going to need to know which block it's in. And here's some simple code where I've tried to explain what each thread in pseudocode, which is going to explain what's going to happen. We're going to start, in this case, with assuming there are 8 threads in a thread block. We'll get 8 of them to load up, 1 value each, and then we get very aggressive. This is the walking threads. You know how in The Walking Dead you go from 8 characters to 4 characters, 2 characters, and then they start adding more characters back in, because otherwise there'll be no characters left. In this case, the walking threads. We're going to start with 8 threads that are active, and then we're going to kill half of them, and then we're going to, all those 8 threads will load value into shared. We'll kill half the threads. The 4 remaining threads will do the addition, put the result in shared memory. Then we kill half the remaining threads. We'll have 2 threads left. They'll do the addition in shared memory. And then we'll kill the second thread. And we've got last thread standing. We'll do the last addition. OK? So it's a classic tree reduction. We're not doing a classic binary tree reduction. We're just doing a classic half-and-half tree reduction, because it's just a lot easier to do with the indexing for that. So in pseudocode, while we'll count the number of threads, each thread will load a value into shared memory. This will be a shared memory array, and this is only visible to threads in this thread block. While number is alive is greater than 1, we're going to have to synchronize, because we have to make sure that all the writes to shared memory are completed. If we had less than 32 threads alive, then we can chance our arm and rely on the 32-way SIMD concurrency. But that's a dangerous game, because it's not future-proof. There are indications from NVIDIA that the 32-way concurrency is not a given in future revisions of the architectures. So we're going to synchronize. We're going to kill half the threads. The half that are alive are just going to do 1 addition and store the result. Keep repeating until we've killed all but the last thread. And then the last thread standing, we could have chosen an arbitrary thread because the value is in shared memory. The last thread standing is going to write out 1 value that comes out of that block reduction. OK? Beautifully simple idea. And here it is in actual CUDA code. Remember, there's an implicit double parallel for loop outside of this. We're going to allocate some shared memory. It's designated to shared with this annotation. Each thread figures out where it is in the global thread array. We're going to initialize the shared block to 0. In this case, it has to check that it's a thread that should really participate in the load, because it might be at the end of the thread blocks, and it might just be some extras we don't need at the end. And then we start the reduction. We're going to say, how many are alive? Well, that's the number of threads in the block. What's our thread index? I'm going to synchronize, make sure all the threads enter here before any leave. Then I'm going to kill half the threads, and the remaining half are going to do the reduction. Does that look complicated? Conceptually, it's not that difficult. The details you have to pay attention to are the use of shared memory and the use of the barrier. That's it. Shared memory looks and acts just like regular memory, except you have to remember all threads have access to the shared memory. OK, and I've included a reduction example, and you're welcome to look at the actual code, yes?
Yeah, I had a question. So what's the difference between the global and shared declarations in that example?
Right, so in that case, the global designator was for the kernel. That basically says it's a kernel that's going to be compiled for the device. In this case, the shared means that it's shared memory local to the core. There's 2 types of shared memory. The shared memory that's collocated with the core, and the shared memory which is global shared memory. But you don't want to get global shared memory confused with the global identifier for the kernel. Right? Yeah, the nomenclature is wildly inconsistent in terms of what means what and when you decorate the code. OK, so I thought what would be good is to do a little example using the John Conway's game of life. Now I've created a serial reference code, and it's straightforward and mechanical process to take that serial code and make it a CUDA code. Recall John Conway's game of life. You start with a rectangular board. You did an example on this already with MPI, right? We're not distributing this board amongst multiple processors. We're pushing it onto a single GPU. Okay? I've got the skeleton codes in the exercises directory, and there's a serial implementation, and I think I put a skeleton for the CUDA. The one thing that's really, so when you look at your code that you're thinking about turning into CUDA, you really need to identify the computationally heavy part of the code. Profiling, you've already seen profiling is to determine what should be parallelized previously. This is the update step where, given a loop over the rows and columns of the board, then you find out what the neighborhood sum is, and based on the value of the sum of the neighbors, you decide whether the board entry at row column RC dies, stays the same, is born, or dies, right? That's the nature of the Conway game. So if you run the serial code, it will look like this. I should type faster. So cloning, get the thing. You've already done that. So while we're watching that, the question I have for you, would you like to do this exercise individually? You do the coding, or I do the coding and you help me? So you suffer or I suffer, your choice. I hear me suffer. Is that a consensus view? Okay. But you're going to have to help me out with the specific calls that I need to inject into the code to make sure it's going to work as a CUDA code. So there it is. It ran while I was yapping away. OK, so that's the code. OK, so you can feel free to ignore what's going on and code it yourself. But because of the pressure on time, why don't I just do this? OK. So this is the code. It's effectively a serial code. I've just done one thing, which is I've included hints to myself as to what I need to do to make it CUDA-worthy. OK. So let me make this as large as possible. I'm going to start at the main program. So at the main program, all I'm doing is translating the arguments. CUDA does not need to know about that. I have an init function. I have an update function, which runs one step in the game. I've just done a flip-flop so that I start with the board, I write to a second array, and there's a reason to do that, because if you think about the update formula, if I did an in-place update, then I'm not playing Game of Life, I'm playing Gauss-Seidel Game of Life. I'm doing an in-place update of the board, and it wouldn't be the proper Game of Life rules. So I have two boards, old board, new board, and I'm going to take my existing board, and I'm going to write values to the new board, and I'm going to flip the game. So I start with the new board and write to the old board. So that way, I'm just going to run double iterations. OK, so the first thing I should look is the update formula. That's that piece of code we just saw a moment ago. OK, so the first thing I have to do is yes?
I'm confused. Which file is this?
Oh, this is in life.c. Oh, sorry, this is in exercises, life, CUDA, main.cu. Yeah, sorry, I should have called it life.cu. And notice it's a .cu file.
Which is not the serial file. I thought we were looking at the serial.
Yeah, that was where we started, and I just did a little prep work to get us to main. You can start with life.c if you feel like it. OK, so first of all, I have to do is I'm going to test your memory as to what needs to be done to this code to make it a CUDA kernel. Yes?
You need to do that global declaration?
Yes, that's right. So I need to annotate this and tell the CUDA compiler that this is, in fact, a global i.e. kernel function. Okay, simple as that. Nothing else needed there. Now, again, I need to map from this for loop structure into a threaded for loop structure, parallel for loop structure. So what do I need to do?
Know which part of the board our block will be working on.
Right. So is this for loop going to survive? Are these for loops going to survive? So these guys, nodding, shaking their heads, they've already created a mental map. They've decided they're going to have one thread. I assume this is what you decided. You're going to have one thread update one value in the board, right? So instead of having this for loop, we're just going to have a thread that's responsible for updating one value in the board. And then we're going to repeat that operation everywhere, right? So we need to somehow translate the thread index values into coordinate values, okay? So how can I find an index into the two-dimensional board from my thread index and block index?
Grid size multiplied by block, like block index plus thread index.
So block size times block ID plus, and then that gets me into the offset. It says how many blocks along in the board I need to go. And then I need to find out where in each block I am. So I'm going to use thread IDX. That tells me what the offset should be for that thread in that block. Okay? And I've done that kind of the wrong way around. So this should be column, because I'm thinking column major. And in row major, I can do the same thing, but instead of using the x coordinates of the block and the thread, I'm going to use the y coordinates. Okay? So already in my mind, in the crazy place inside here, I've already established a map between the two-dimensional blocks of threads and thread blocks into the board coordinates. And I've made a one-to-one map between the block and my threads. Now, none of you paid attention too closely, because where does my row index start? So I've embedded my game of life in the board, but I've started one in, because I don't want to have to deal with boundary conditions. Okay? So I really need to make those one indexed. So I'm just going to shift those indices by one. Okay. So I've done this check. I've done that, okay? Notice I just get rid of that loop structure entirely. It's no longer necessary, because we've got a map between the iterations of the loop structure into thread space. And then each thread is responsible for one iteration. And it's not a unique map. I could have chosen all sorts of different ways to map between threads and the board. This is just the intuitively most obvious. None of that changes. None of that changes. And I was kind of sneaky here. If you look at the way that expression for the update formula is written, you'll notice it doesn't involve any branching. Just, I didn't notice this when I wrote this expression, but it's my habit now to avoid if statements. If I can avoid an if statement and replace it by a Boolean operation, then I can avoid branching, and branching is death for parallelism. Okay. Okay, so we've now completed the update formula. Yay. Okay, so we have to make sure that these row and column values are in range, because we may not have neatly tiled this for loop. So we should check that if row is less than n rows minus 1, which is basically the upper check on that for loop, the upper bound on the for loop. At some point, I have to decide, I have to move the data to the GPU. So let's do that part now. Let's migrate the data. So first of all, I have to allocate, yes, hello?
Not really a branch, right? There's no branching in code. It's just some threads doing it, the other threads don't.
Some will do non-operation, so it's a very shallow branch. In general, we really try to avoid wasteful branching. This is not particularly bad. It's slightly bad because, and we haven't discussed this yet, it means that some threads will be performing non-coalesced access in memory. But in general, it's the least worst of the branching. Okay, so we better actually send some data to the device so it can run the update formulas. Okay, so the first thing we need to do is allocate space on the device for these arrays. What is the CUDA API for doing that allocation? CUDA malloc, right? Now, if we look at the definition of this function, I've preset those double star pointers to the board and the new board. So all I need to do is do a CUDA malloc and pass in cboard, and I need to specify how many things I want to allocate. And we're using an integer board, so that's it. Cut and paste. Okay, so this is allocated the space. And then I need to do a CUDA mem copy. Okay. So it's reverse direction, so I'm going to copy from board to that, and I need to say how much of this. Oh, and the other thing is it needs the pointer, not the pointer to the pointer, so we'd better give it the pointer. N rows times n columns. And the last thing we need to provide to CUDA mem copy is what? Direction, where we're moving the data to and from. So it's CUDA mem copy. What's the next part? Where is the data right now? Host. Where do we want it to go? Okay, so that's basically the thing we need. And I'm just going to cheat and just send the same thing to the new board. Okay, so we've written the kernel that's going to process the board, update the board. We've moved the data to the board. At the end of the iterations, what are we going to have to do? We're going to have to copy the data back so we can print out the board. Once we've done the malloc and the memcopy, we've got the kernel that's going to be executed. We actually need to execute the kernel, right? That's the next thing we're going to need to do. Yes?
Does that second board in the second line need to be new board also?
It could be, but I think I was being lazy. I didn't necessarily populate new board properly.
So that second mem copy is copying new board into the same?
From board to new board. It goes right to left. Yeah. If you remember nothing from this except for CUDA malloc and CUDA memcopy, the thing you need to add on top is it's reverse. So you go right to left. So you can literally read it. CUDA memcopy hosts the device this many bytes from board to new board. And notice those are double star pointers for cboard and board because this function is initializing those pointers. So next thing is we should actually launch this kernel. So there's the update kernel. So we have to specify, and I've done some of the work here already, specify the size of the blocks and how many blocks we're going to use. So I've decided I'm going to use 16 by 16 blocks. And dim3 is a C++ construct. So this will be the thread block size. So this basically says T threads by T threads, 16 threads by 16 threads. We're going to use that and pass that into the wacky invocation of the update formula. So that raises the question of how many blocks, let's call it block rows and block columns. How many blocks am I going to need to use in the x direction, in the columns direction? How many in the rows directions? Well, I need to do division, but I need to round up. So I'm going to use the handy formula for interdivision with rounding up, which is, this is n columns plus t minus 1 divided by t. And if you stare at that formula long enough, you'll realize it's integer division rounding up. And I'm going to do the same thing for the number of rows. And this is, of course, predicated on we need enough blocks to cover the rows and the columns. So to initialize that, I'll say this is going to be the fastest one in the first entry, the slowest index running the second direction, and there we go. Now, I need to bake this thread block and grid block information into the launch for the kernel. So how do we tell the CUDA runtime how many threads we're going to need? The wacky syntax, the launch parameters, are encoded with this triple, and I think it's grid dimension first, that's how many blocks, and block dimension second, that's how many threads per block. I'll need to do that twice. Okay. There's one more thing we've done. Remember the canonical CUDA code is allocate space on the device, copy data to that space, run the kernels. What's the last thing we need to do? Synchronize, sort of. Copy it back. I like the so that way is to the left is copy it back to the from the device to the host, because remember it's on a separate device. And I have this print function which is going to play that role. So we're going to do again CUDA mem copy, and you're going to tell me what to write here. Remember the device stuff is C underscore, that's shorthand for CUDA board. Right? And we want to copy from CUDA board to the regular host board. Yep. Pardon? No star, because it's just a pointer. C board. Yeah. And then, exactly. And reading from right to left, copy from device to host this many bytes from this, starting at this pointer on the device to this pointer on the host. That is a source of an enormous amount of angst because people get this wrong. The direction, the pointer source, pointer destination. And then I've already got the code that will print out from the host. Now the data is resident. Now, implicit in this is I didn't explain what the CUDA mem copy does in terms of blocking. When we ran that kernel, that was a non-blocking request to run that kernel. The CUDA mem copy is going to block until all of the kernel run requests have been satisfied. And it's going to block until the data is copied back to the host. Okay? So you have to be careful about your mental model that you have to understand that this is, in fact, a blocking copy request. Blocks on the queue and the memory copy. Okay. Is that it? Last thing I have to do is check, did I put CUDA.h? Yes. Another standard issue. You forget to put the CUDA.h. Okay, let's try it out. Who thinks it's going to work? Nobody. So MV CUDA compiler, we'll give it the main. You have no faith at all. Let's run it on the small board. Ha! It worked. It's a mechanical process. You just have to remember the three critical phases. Setup, that's port the data to the device. Process, just make sure the kernel's running on the device and it's doing what you think it's doing. Copy back. As long as you get those things right, it'll work. Let's try, yep, ran on a 32 by 64. It's that simple, right? There's no magic here. There's no fairy tales, unicorns, rainbows. It's just a mechanical process, yes?
But did you release the memory that you allocated?
Damn you. CUDA free. So remember, I've allocated that memory on the device, and it's going to stay there until I CUDA free it or my program exits and terminates. And then it'll be collected, right, recovered. What did we do? CUDA memcopy, sorry, CUDA malloc, CUDA memcopy, wacky launch syntax where we designed the thread array that we wanted to use. The piece of code that goes at the inner part of some nested for loops, which was our target application. CUDA memcopy the data back. Done. Right? Don't let anybody tell you that was difficult. The conceptual part of it was we created a map between the threads and the work that needs to be done. But that's at the level of a parallel for loop. What I've showed you is how to program CUDA GPUs using embarrassingly parallel kernels, or even using shared memory and synchronization to do collective tasks that are collective at the level of thread blocks. Okay. But what happens if you don't happen to have an NVIDIA GPU? And let me tell you the sad tale of Blinky the laptop. Blinky was my laptop until a couple of days before the last AT-PESC workshop. It was one of the last Apple laptops that had an NVIDIA GPU, and it died. So a moment of silence for Blinky. All I was left with was a flashing folder which said, "I've lost all your files." But more importantly, I'd lost my laptop with an integrated NVIDIA GPU. So if I'd just written CUDA code, I'm screwed, right? My development platform's gone, my small run case platform's gone. I then have to rely on my desktop, workstation, and clusters, right? So my primary developer point has gone. So I can no longer develop CUDA on my laptop. Bugger, right? So think of this as a warning sign that you don't want to necessarily overinvest in one specific platform. And I'll talk about the different approaches to guaranteeing that even if there's an apocalyptic meltdown of OpenACC standards or OpenCL standards, CUDA goes away, you want to hedge your bets and be able to program, still be able to program, even if those standards evaporate, and it's possible they will. Oh, and the other thing that Apple did recently, much to my chagrin, is they transitioned to the Clang C language compilers, which no longer have OpenMP as a default feature. So if you're developing OpenMP on OS 10, you now have to go through some pain and install your own GNU compiler collection just to get OpenMP access. So we have single point of failure issues. There are some options for cross-platform programming. OpenMP. Pre-OpenMP 4.5, you could use these to program Intel x86 platforms. Now I know Tim Mattson said yesterday you can use OpenMP to program GPUs. That's a wildly optimistic claim. If you try now, today, to do that, you will spend a good deal of time trying to get the OpenMP front end and the GPU back end to communicate properly. It's technically possible, and he could mention one group in Germany who'd done this. So it's on the roadmap. I wouldn't claim it's mature in any way. OpenACC. It's gone from a multi-compiler support to very limited number of compilers that will support OpenACC. It was in some sense bad news when NVIDIA bought PGI, because now you've gone to essentially a single provider for OpenACC, sort of. CUDA, not portable. OpenCL, on the other hand, is portable. So next I'm going to talk about OpenCL. It stands for Open Compute Language. There's a standards committee, the Kronos group. There's a fascinating backstory as to how OpenCL came along. OpenCL is more or less a product of Apple, which sounds weird, but Apple saw the success of CUDA and decided that they wanted to be able to build they wanted to build an acceleration framework for OS X, but they didn't want to have a single vendor behind it. They didn't want to have CUDA underpinning OS X because suddenly the price for the GPUs and the laptops goes way up. They wanted to be able to play market forces and play AMD versus CUDA versus NVIDIA. So they forced a marriage of inconvenience between effectively NVIDIA and AMD through the OpenCL Standards Committee. They brought a bunch of other people in, but the most important participants are AMD and NVIDIA. Now, once you get a committee involved, the complexity of the specification for the standard just goes way up, and it goes way up because now you've got multiple platform types. You've got multiple architectures that you're going to target with OpenCL. You're going to be able to run on FPGAs, field programmable gate arrays, CPUs, GPUs, embedded processors. It's going to be problematic, and that's what, in some sense, that's how it turned out. Now, just to give you a little of backstory, as I said before, a lot of this general-purpose GPU programming comes from PhD work at Stanford. So about 2005, they had a working solution. It wasn't particularly usable, the Brook solution. Nothing really happens until NVIDIA releases CUDA, AMD releases Stream, which didn't really go anywhere. And then from 2008 to mid-2008, Apple proposes an OpenCL working group, and we get to a release of the standard within about 6 months. So how does a working group, which is a committee of diverse stakeholders, how do they produce a standard in 6 months? Sorry?
One of them is like having final order.
The product still has to be produced. So how do you produce something in 6 months? Think about your PhD in the last 6 months. How much did you do? Epsilon ball around 0, right? So how does a committee produce something, basically a standard, within 6 months? They borrow, right? Which I think was what you were muttering. They borrow. Steal, borrow, it's all the same. So who do they borrow from? Well, Apple basically wants CUDA, but with multiple vendors. So you borrow CUDA. So let's see the translation between CUDA and OpenCL. The terminology, this is very similar. Kernels, host programs, threads become work items, thread blocks become work groups. Part of that, making the generic translation between thread and work item, is because they don't necessarily want you to think of a work item as an actual thread, because it may not be a thread, right? And a thread is an overstatement of exactly what is happening at the level of a floating point unit on an NVIDIA chip. It's not a true thread, okay? It's just one instance of instructions flowing through a SIMD unit. So it's not really a thread. So we call it work item, work group, and grid becomes, that's the block, the grid of blocks becomes ND range for n-dimensional range. The committee got one thing right. They changed those horrible intrinsic thread index, block dim, block IDX, block index variables that come out of nowhere, become API calls. Get local index, get global index. So there's less dicking about with thread indices and piecing together multiple ranks to get global ranks, right? So that's already baked in. I prefer this one, that you can basically just say, what's my index locally or what's my index globally? That's a lot easier than messing around. Grid dimensional becomes get num groups, block index becomes get group ID, block dim becomes get local size, grid dim times block dim becomes get global size. So it's a much more rational way to find out what your rank is, what the size of the problem, what the size of the thread array is, and so on. Decorations of kernels. Underscore global, underscore, I don't know why CUDA likes underscores so much, but they put them everywhere. OpenCL becomes underscore kernel, double underscore kernel. A device function just becomes a function. We haven't talked about constant memory space. Device variable becomes a global variable. So implicit in our definition of the kernels, we've just been using raw pointers, but implicitly we're actually saying device pointers. Here we actually have to say what memory space the variables are, or pointers are defined with respect to. And then shared, unfortunately, becomes local, which is very unfortunate because in CUDA, there's a local memory space, which we're not going to touch. Okay, so the memory model, which we haven't really dwelt on yet in sort of detailed graphical form, is the same. You can actually map from image on the left, which is CUDA memory model, to OpenCL on the right, which is basically the OpenCL memory model. Okay, so the contortions to go from the CUDA syntax to the OpenCL syntax, that's pretty straightforward. That's basically just, it's just an exchange of syntax. However, because we can now program pretty much anything, you can program your calculator with OpenCL, you can program an embedded device inside an automobile with it. Now we have a problem of choice. And it gets compounded by, because you might not just have one installation of OpenCL, you might have several different vendor instances of OpenCL on any given machine. You might have Intel's implementation. You might have NVIDIA's implementation. You might have AMD's implementation. So you have to choose, basically, the vendor. So you'll choose, you use CL get platform IDs to choose a platform. That's i.e. the vendor's version of OpenCL. Once you've chosen the platform might refer to 6 different devices that are operable through that version of OpenCL. So you might have a machine, and it could have an AMD GPU, an NVIDIA GPU, an Intel CPU. Then you might have multiple versions of OpenCL sitting on that machine. You might have an Intel version, you might have an NVIDIA version. And then you're going to choose the manufacturer's version of OpenCL, and then that will give you a list of possible devices. So you need to choose the device from that list that are compatible with that platform. Once you've got that device, you need to create a context. That's basically the manager that's going to allow you to interact with that device on that platform. Once you've got that manager, then you need to actually create one or more command queues. That's basically where you inject these kernel requests onto the device. So there's no default queue because there's no default device, there's no default platform. CUDA is great because there's always a default platform, there's always a default device, there's always a default context because it's all NVIDIA. But we have the problem of choice, so we have to create a queue so we can inject kernel requests. If we look at the comparison between the host code APIs, so in CUDA, we'll ask for a CUDA, we'll use the CUDA header files, OpenCL. Apple had to be different, and you have to use their header file. Anybody else, you just use CLCLH. So on OpenCL, you have to set up a platform. CUDA, not so much. So you'll give a list of, you'll say, give me the first 100 platforms, and it'll give you a list of platforms. CUDA, you can choose to set a device, or you can accept the default device. OpenCL, you're going to get a list of device indices, and then you're going to choose one of those devices by some means. You need to set up a context so you can interact with the device. CUDA, nothing to do. OpenCL, you have to create the context, which you feed in the device and say, I want the context on that device. CUDA, nothing to do because you don't need to set up a default queue. OpenCL needs to set up a queue. I hope you're beginning to see why OpenCL hasn't caught on so much. Because of this combinatorial explosion of platform devices, context queues, and so on, we're going to actually have to compile the kernels at runtime. You might be the first person to ever run that kernel on that specific combination. So you're going to have to actually build the program, which is a multi-stage process. So you're going to create a program with source. You're going to basically give this function a string and say, please build a program. So you're going to create the program. Then you're going to build it. Then you're going to check if there are any errors, because again, your program won't be perfect. You're not like me. You're not going to write the first time. It's not going to be correct, right? Then once the program's built and error-free, you're going to create a kernel. So this is the sequence of commands for creating a kernel. Are we there yet? No. We've built the kernel. Next thing we need to do is allocate space, because again, like CUDA malloc, we need to use the CL equivalent. We need to create a buffer, or buffers. Once we've got the buffers, we're then going to have to actually figure out, before we call the kernel, we need to set the arguments that are going to be passed to each kernel. OpenCL is library-based. There is no special OpenCL compiler for the host code. So when you call a kernel, you don't use magic syntax. It's a library call. You pass it the kernel object, and it's going to assume you've associated arguments with that kernel object. So you need to basically feed in the arguments one by one before you can launch the kernel with NDQ range. So you'll set the kernel arguments one by one. Then you can queue, or you need to specify the number of threads you want, and then you can call the ND range or NQ ND range kernel. And if you want to wait for it to finish, then you'll call CL finish. So here's a comparison. CUDA malloc top, create buffer bottom. Launching the kernel at top, simple in CUDA, a little bit more complicated because we need to set the arguments in OpenCL, devise the thread array, and then queue the kernel. Notice, instead of using wacky syntax like you do in CUDA, you just use an API call to call that kernel. The one thing that's easy in the comparison is kernel language. Left, CUDA kernel, right, OpenCL kernel. It's a one-to-one map, because remember, OpenCL borrowed heavily from CUDA, especially at the kernel level. But frankly, OpenCL has a bit of a bad reputation. You can probably see why now, right? CUDA has a richer ecosystem of tools and libraries. It was there first. So it's kind of like Sony Betamax versus VHS. VHS was a crappy standard. Sony Betamax videotapes. Sorry. Okay, magnetic storage device for video. Anyway, so CUDA was first and has more extensive documentation than tutorials. There's a large community that's using it, basic because it was first, has got better tools first. You have to deal with the platform device context and queuing. Setting up kernel invocations is slightly trickier because you have to basically manually add the arguments to the kernel one by one. But more systematically, you have competing vendor priorities. Each company will devote a limited amount of resources, and they have a tendency to devote their resources to their favorite compiler solution for their favorite hardware. So Intel will invest in OpenMP. We saw that yesterday, with a certain amount of vitriol directed towards CUDA, right, and OpenCL. NVIDIA will devote resources to CUDA, and OpenCL suffers because they don't devote as much. They can't devote as much to OpenCL as they do to CUDA, so it trails. There are also some other features, like if you look at the details of the efficiency of the OpenCL implementations, then they suffer in comparison to some of the vendor preferred solutions. So OpenCL, in many cases, is the second best way to run on a platform. Intel, you might use OpenMP. Under certain circumstances, Intel's OpenCL is good, but I've heard Intel folks say it shouldn't be as good as, OpenCL shouldn't be as good as OpenMP on their CPUs. NVIDIA, CUDA is typically better. Sometimes OpenCL is about the same, and so And there are constant rumors about vendors end-of-lifing support for OpenCL. So although it is the obvious solution for portability and to some extent performance, there's this uncertainty about it as to whether it will continue to be supported going forward. On the other hand, it offers runtime compilation. You probably didn't really absorb that, but it's very important for runtime optimization of kernels. Because you can compile a kernel when you run it, you know all the parameters for it. So you can do heavy online optimization. You can tell the compiler, the OpenCL kernel compiler, you can hard code all the parameters without templating. So you can know exactly, the compiler knows exactly what to unroll, how to unroll it, and to get best performance. So it can actually deliver good performance. It's library-based, so no special compilers are required. That's pretty cool. And it's vendor independent until the vendor decides to stop supporting the project. So that is really quite cool. Let me check. I think I've got time. And we don't need to see that. OK. So, yes?
Just a rapid question. Is there an implementation, virtual implementation of OpenCL?
Well, it's library-based. So the host API you could call from Fortran, because it's all library calls. And it's all generic C library calls. So you can call, Fortran can call C, that's for sure. The kernel language, I think there are Fortran kernels, but I'm not sure. I'm not going to commit to that. I'm not a Fortran guy, so I'm sorry I can't really commit to that. But so on the one hand, you have CUDA for GPU programming. You have OpenMP for CPU programming, sort of the optimal solution, or you have possibly slightly suboptimal OpenCL, right? And it's a very unpleasant thought that you should have to write 3 different versions of your code. Nobody wants to write the first version of the code, let alone the other 2, right? Imagine writing your thesis code 3 times. Nobody wants to do that. So we've got to talk about portability. So we've got the standard programming models, but we can achieve some level of portability through some middleware. So if you really like CUDA as a programming model, if you're willing to put up with the idiosyncrasies of the kernel language, of the launch specification, and so on, then you can use these intermediate tools to translate to other programming models. So for instance, actually independent project at Virginia Tech called Cuticle, C-U-T-2-C-L, Q, will do a source-to-source translation between your CUDA and OpenCL. Hipify is a new project out of, I think it's either AMD or the HSA Foundation, that will take CUDA code, mangle it into AMD's sort of portable threading model, which can then be used to program AMD GPUs or NVIDIA GPUs. You can go well into the weeds and use the Ocelot code to translate the NVIDIA binaries into AMD binaries, and so on. Now, that's if you like the CUDA programming model. Not everybody likes that. Because again, it hides that parallel for loop structure. It's not intuitive. You actually have to think about it. It's not hard, but there is some conceptual leaps. Yesterday, you saw OpenMP and by extension OpenACC, which are effectively twins, or at least cousins. They have varying level of support for accelerators. I'm going to put that generously. The problem I have with them, and you may have noticed this yesterday, is that in one sense, it's one thing to decorate your code with directives that say, make this a parallel for loop. It's another thing entirely where you have to go through your code and decide which array gets moved to the device at which point. So you have this problem that there's the host and a device maintain separate memory spaces. Even if they're virtualizable, they're still separate memory spaces. To get good performance, you manually need to make sure that data is being moved at the right time. NVIDIA's making progress in doing just-in-time memory movement using dirty pages and so on that you saw previously. But in the end, if you do a careful job of moving data, you've now got an extra level of complexity because you're going to have to add data directives to say, move to host, move from host to device, and so on. So in terms of writing cohesive, coherent, maintainable, productive code, you've just created a massive problem going forward because code is not static. Code gets changed. So you sweep through the code once and put the directives. Somebody starts changing the code. It's going to have to go through again to make sure you've got a coherent data model. This is very problematic in terms of long-term support, sustainability. And if we talk about maturity, I'd say in terms of accelerator programming, CUDA is pretty mature, OpenCL is pretty mature. The other packages are, other efforts are much less mature. And if you look at ease of use, I'd say CUDA is pretty easy. We did a demo, relatively complicated piece of game of life or the reduction or the serial operation. That's pretty straightforward. It's just a matter of move some data, do some stuff, move some data back. OpenCL, because you have the extra complexity, it looks like it's slightly less easy to use, but this is just my opinion, of course. So the big question in HPC right now is MPI plus X. What is X? And each vendor would like you to solve for X being their solution. OpenMP, CUDA, OpenCL, TBB, Silk, Silk Plus, whatever their favorite solution is. But I say, don't choose, okay? We'll delay that choice until the moment we're running the code and need to do some heterogeneous computing, where we need to actually engage an accelerator or device, whatever. That's where my stuff comes in. My pragmatic approach to solving the MPI plus X problem, which is essentially don't solve it. Create an abstraction, an interface, and hide the CUDA, the OpenCL, the OpenMP warfare behind an abstract wall so that whatever games the vendors play, the standards committee plays, we're oblivious to them. All we have to do is at runtime translate our device-independent, vendor-independent code into code that they understand. And just delay that decision as long as possible. In fact, I could compile up our kernels 3 different ways and choose the best one. And then the person running the code doesn't even need to know what the best platform is or what the best vendor solution is. We'll just choose it arbitrarily out of the list of vendors based on performance, not based on philosophy, not based on whether you prefer OpenMP, that's your baby, that's the one you're going to say, and you should say, don't ever do CUDA. That seems like a limiting choice. Just choose, at runtime, the best tool for the job, right? And then everything else falls into place. You don't have to play any games, choose favorites, whatever. So we created this library. You can program in the front end, the API, using native Fortran, native C, C++, Julia, Python. We'll have differing level of support. I'm a C guy or C++ guy. Those probably get the most attention. We have built our own parser, and we've built a couple of kernel languages. But we can also inhale CUDA or OpenCL kernels. And they will automatically get translated through an intermediate representation into P-threads, parallel threaded code, or OpenMP code, or OpenCL code, or CUDA code. Doesn't that sound better than actually doing it yourself, right? It seemed to make sense to us. And then we can go choose the best combination of thread model and platform. So there's a single unified library. At runtime, you can choose which thread model you want to use. It's portable, it's lightweight, it's not a huge code. Self-contained, it has 0 dependencies except for the compilers. That's all we need. Access to the NVIDIA compiler, access to an OpenCL capable compiler, access to a OpenMP compiler. That's all we need. It does not auto-parallelize, auto-optimize, auto-layout, auto-distribute, or do low-level code. So it's not a magic solution. It just solves the problem MPI plus X, which X. Just choose the one that works best at runtime. There's a close-up. So it's a very simple, it looks complicated, but essentially the action is very simple. Now, the instructions for downloading it are here. We have, it's all open source, it's all available, nothing's hidden. There's just a little bit of a setup phase. So why don't you try installing it? You might want to do this on the head node. And then I'll show you an example where we can just switch how a kernel is handled at runtime using the Ocker code. Okay. So let me tell you how we position or how we view Ocker, where it sits. So the thing we're talking about is the Open Concurrent Compute abstraction, called Ocker for short. And we'll tell you how it sits in sort of the canonical hierarchy of portable solutions. So at the top, we have some national lab packages for array management or array processing with GPUs, accelerators. So COCOS and VexCL are instances, but there you would use a high-level, more or less pre-canned operations or streaming operations like vector operations that can be specified through entry-wise operations on those objects. Similar with Raja, except it's using C++ lambdas, so C++ 11 features. Ocker, we are going to specify kernel languages, although you can still use in CUDA and OpenCL kernel languages. And then we will do online translation to whatever backend you want. CUDA call is more of a static solution where you're doing source to source. You write code in CUDA, and then you use CUDA call to do that translation. But that's less online, it's more of an offline solution, and so on. So you can go down all the way down to the bottom where you're doing binary translations. So the first thing to introduce is the kernel language. The kernel language puts back into CUDA. So NVIDIA took out the parallel for loop structure and made it intellectually slightly harder to understand what a kernel is doing, because you have the body of the code with no context, right? You've taken the for loops out, the parallel for loops out, and all you're left with is the implicit for loop structure. So when you look at a piece of code, it's actually can be quite difficult to understand what the code's doing. So we just put it back in. We put in for loops with an extra argument to say where in the parallel loop hierarchy it is. We have 3 possible outer loops, 3 possible inner loops. You don't have to have all 3 of each. You can have 3 inner loops, 1 outer loop. So now it looks like serial code with just a minor decoration in the for loop. And all kernels will look like something like that. The outer loop iterations will get mapped to work groups. The inner iterations will get mapped to work items. So that's sort of the structure. Now, because we have our own code parser, because we can transmute our own kernel language into whatever we like, we'll actually let you write multiple kernels, multiple outer inner block structures within the same function. So you don't need to tear up the code into kernel, 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 kernel. You can actually have one kernel that encapsulates multiple subkernels. So it's a bit more flexible in design than a standard CUDA kernel. We can put in conditional statements, and you can actually decide whether you want to run that kernel or not based on conditional expressions. And we also expose shared memory, and we have a notion of an exclusive variable, which is synonymous with a thread private variable. We have a Fortran version. I know there's some Fortran heads in So we actually do accommodate Fortran people. However, I would say that support is somewhat broken. We desperately need a Fortran person to come in and do some rigorous testing for us. We have a Fortran API, and we also have a Fortran kernel language. It's slightly decorated Fortran, where again, you need to specify whether a loop should be counted as a block loop or a thread loop. But it's a work in progress. We can also take CUDA and reverse engineer it into our intermediate representation, or we can take an OpenCL kernel, reverse engineer it into our own intermediate representation. We've substantially streamlined the host API compared to the OpenCL API, but it's slightly more complicated than the NVIDIA API because we have more models to deal with. So we'll typically do stuff with host variables, okay, and this is compiled with a regular compiler, a regular C++ compiler. We have the notion of an Ocker device, Ocker kernel, and Ocker memory object. We can set up the device. At runtime, you can choose. In this case, I've chosen OpenCL, platform 0, device 0. But I could have chosen CUDA, device 0, or CUDA, device 1. Or I could have said OpenMP. It's as easy as that, because all the magic translation happens behind the scenes. So suddenly your one code becomes those 3 codes you didn't want to write. We use a devices in charge of doing a malloc. We can use copy from, copy to. We can build the kernel from source. Again, we do need to build at runtime. But we're also doing OpenMP, build at runtime, OpenCL, build at runtime, and CUDA, build at runtime. So we can bring that nice feature in OpenCL where we can bake in all the parameters for the function so we can maximally optimize the kernels because they get built at runtime with maximal information. And then, by some by some C++ function magic, you can actually call the function as a regular function. No wacky it's CUDA syntax, no ND, Q, range, Q, whatever the thing's called. Nothing magic. You just call this thing we built here as a function. And then we'll copy a result back. So it's hard to see, but has anyone noticed anything interesting about this call? Is there something I didn't need to specify? In CUDA, what did I need to specify when I launched a kernel? Block size, grid size. In OpenCL, I needed to do that too, right? Where did I move that information to? To the kernel itself, where it belongs, right? So this is a problem with OpenCL and CUDA, where you have the core of the for loop structure divorced from the bounds of the parallel for loops. So we moved the specification in CUDA and OpenCL, that's the specification of the parallel for loop structure is moved to the host, which is very awkward, right? Because you need to coordinate these things. But we've baked it into the specification of the parallel for loops in the OKL kernel language. So there's no need to actually specify it here because it's already baked into the kernel itself. And there's some examples. And then the kernel language, the kernel itself is just this piece of code. We've got the decoration down to, well, we have to specify it's a kernel, and we have to specify which are outer loops and which are inner loops. Inner loops get mapped to threads in thread blocks or work items in work groups, or in OpenMP, we just make those serial inner loops. Outer loops get mapped to thread blocks in CUDA. Iterations become thread blocks in CUDA, work groups in OpenCL. Or in OpenMP, we use a different strategy, which is we use chunking. So we chunk up the outer, we merge the outer for loops, and then we chunk them, just as you would have seen in OpenMP. And we've got multiple native host codes, C interface, Julia interface, Python interface, MATLAB. There was no interest in running this in MATLAB, so we've nuked that. But if anybody's interested, let me know. But it was kind of cool. You could run OpenCL or CUDA or OpenMP just from that lab. If we look at the serial kernel, this is a Poisson update formula, or Poisson iteration, I guess, X or Poisson. Here's the CUDA version where we strip out the for loops. We just left with the inner part of the loop. OpenCL is the same thing. Here's the intermediate representation you don't need to worry about. And here's where we've gone from the serial loop through the kernel, OpenCL kernel language, where we just do an explicit partitioning of those for loops, right? So everything you need to know about this kernel is in here. There's no magic external intrinsic variables. Everything's baked into the description of the for loops, and it should not be mystical. Behind the scenes, we've got a lot of machinery. So what's the machinery doing? Well, because we're doing runtime compilation for all those different platforms, that can be burdensome. If every time you have to run the program, you have to recompile the binaries for the kernels you want to call, that's a real problem. And we ran into this on the Titan system where you have 16,000 GPUs, you've got 16,000 hosts trying to compile up the kernels. It just doesn't work. So we've got a caching system. So when a kernel's compiled with a set of parameters once, we'll hash it and cache it. So that next time we want to call that kernel, it's a very fast operation to call that kernel. In fact, on Titan, we went further, and we actually, and there's a lot of stuff, magic happening behind the scenes in order to make it happen. OK, so I don't really have time to go through the Conway example, but I'm just going to show you what the solution looks like. 80 PESC 16. So this is the Conway game of life using the Ocker version. And if we look at the main file, where before we had CUDA calls, we now have device object function calls. And we'll build kernel from source. We'll use device malloc to allocate the boards. We did separate off the update kernel into its separate file, just like you do in OpenCL. And then we have an update formula, which just is double-nested two-dimensional for loop. We just loop over the start of each block in the rows and column coordinates. We do the update, done. Okay, and then we have copy tos and copies from when we want to copy to the host or copy from the host. Okay, so it's a very simple API, very simple kernel language, which reunites the notion of the thread array and encapsulates it within the description of the kernel. So when you set up the device, you can choose to basically just pass a string, and the string can be changed at runtime. So I can choose to make it an OpenCL calculation or a CUDA example or a serial example. So let's just run it on my laptop. OK, so whatever mode we're going to run in. So if you saw it real quick, it was using GNU++ a serial, I think it was serial implementation to compile it up. If I just do this. OK, so if I look at my main function, I was using OpenMP. So I was actually just using OpenMP parallelism. It chunks the outer loops of the code. Instead of doing that, I'm going to use my magic wand to make this an OpenCL calculation. Fingers crossed that this works. I'm going to nuke the thing. I'm going to just pass it through. And it's there. It's clear that it's using OpenCL to compile up the kernels. Okay? So what we do is we take that OpenCL kernel language, we pass it, push it through a parser, and it's going to create OpenCL compliant kernel code. Okay? And then that will just execute as an OpenCL kernel. If I just do one more test, I'm going to run this in CUDA mode. Oops. it went too fast, but it was essentially pushing it through the NVIDIA's compiler. And it's compiled it up to NVIDIA, and this is running in NVIDIA's backend. Okay? So we achieve native performance in OpenCL and CUDA through the OpenCL language. It's basically a pass-through. It's a pass-through compilation step. OpenMP, depending on how you structure the code, you can get good performance there. Okay? So when I say don't worry about the details of whether it's going to be OpenCL, CUDA, or OpenMP, it's not that important with the Ocker environment because you can, or the Ocker package, because you can just delay the decision till later. This is some just relative performance of a strongly optimized high-order finite difference wave propagator. The native code written for CPU is the baseline on the left. If it was ported to Ocker, and we actually saw a speed up. And that's because we're doing runtime compilation, so all bounds can be known at runtime, so all loop bounds, and then heavy optimization can be done to speed up the code. And there's another factor here, which is the person who did the porting was the super programmer from my research group, so he couldn't resist just improving their code on the way, right? In this case, we could use a CPU custom kernel, and we get speed up. If we use a kernel that's optimized for GPU, we actually get slowed down because if you really want to program the GPU slightly different from the CPU, and there's some technical reasons for do that, but mostly it comes down to data layout. And then on the GPU, we've actually even managed to improve the performance of this highly optimized industrial wave solver. It's used in seismic imaging. It's a workhorse for oil prospecting. Okay, and so the numbers aren't that important. It's just to show you that you don't take a big hit from using Ocker. We actually see performance enhancement. Discontinuous lurking, which is my favorite thing. Same application, it's for reverse time migration, which is part of the seismic imaging. We can get extremely high gigaflops, reasonable bandwidth, and just to illustrate that in this case, we can run on OpenCL using AMD's GPU, which actually turns out to be much faster than the NVIDIA GPU of the same vintage. And if you look here, the reason I put this up here is because this is NVIDIA's OpenCL and NVIDIA's CUDA. Same platform, identical kernel. There's no reason that the NVIDIA OpenCL is underperforming the NVIDIA CUDA version of this code. No reason apart from lack of investment into the OpenCL compilers. So if you are faced with the AMD, you would just default to use the OpenCL. If you're using NVIDIA, you'd probably choose the CUDA. But it would just you can automatically choose at runtime. Choose the best platform on the best device that you can use. We took a Lattice-Boltzmann code, very weak strawman CPU code, which we sped up 1,000 times. But if you actually look at just the Ocker version running in OpenMP mode, OpenCL mode, different platforms, then we get reasonable speed-ups. So this is a code that's used for modeling wetting of rock. Done this for seismic, for tsunami modeling. Again, different platforms, all automatic, one code. I can report 5 different. So the great thing about Ocker is it's like a paper generator. I can generate results in CUDA and say, there's a CUDA paper, or OpenCL, there's an OpenCL paper, or OpenMP, or then the comparison paper, right? So if I was shameful, I would do that. So we can do all sorts of things, and these are quite complicated solvers. They're not simple, very simple solvers. We can get to quite high level of complexity in code, partly because this abstraction is more straightforward to program with, because you have all the information in the kernel, and you can understand everything in a more global sense. We've done an algebraic multigrid solver, and we've done some standard benchmarks. So there I've just tried to give you a taste of CUDA, an overview of OpenCL, and a description of some of the ways we can achieve portable performance on GPUs. And then at the end, my message is, don't code directly in OpenMP, don't code directly in OpenCL, don't code correctly in CUDA. Choose one of the higher level abstractions where there is direct generation of code, or there's a library level, so that the hard work of making sure you get optimal performance on the different platforms is taken care of for you. So that has been our goal with Orca. There are multiple different approaches to this. We're going to hear about Chapel, I think, this afternoon, which offers similar level of abstraction. And the key here is abstraction. When I first started working in this kind of technical code 20, 30 years ago, we would, for instance, use BLAS. And we'd use code that was littered with calls to Fortran functions with hundreds of arguments, well, hundreds, but tens of arguments. It takes a certain realization you shouldn't do that. You should encapsulate the calls you want to make in reusable units. So already basic software development says never code directly at an interface. Always encapsulate it. My argument is you should encapsulate the threading models. And we've done it in one way. There are multiple ways to do this. Thank you very much.